All right, guys, we're nearing the end. We're almost there. A few sections left. Where we were at last time, we were doing definite integrals. And we saw that the integral of a to b of f of x dx equals f of b minus f of a if f prime of x equals f of x. Like if big F is the antiderivative of little f. And we also saw d dx of a to x of f of t dt was just f of x. These two were two parts of the fundamental theorem of calculus. This top one here, the a to b of f of x dx equaling f of b minus f of a. Another way we could talk about this is like a change in f from b to a, from a to b. But this is the the unsigned one. We don't have this this includes, well, this is the signed version. So like this has, like if f is like, or we have our graph like this and something like this, what we're doing when we do that integral is we're finding the net value here. So like this is a, b, and c. It's a minus b plus c. So it's not really a change. It's a net change. Net change.
Capital F indicates the integral.
The antiderivative of little f.
Oh.
Yeah, if you integrated f, little f, you get big F.
Okay. Making sure.
Like that. So that's actually another thing that they call this. They call this the net change theorem. It's part of the fundamental theorem of calculus. But that's a long way. That's a lot of words, and when you can just say net change. So this is, I'm finishing up just some ideas in 5.6, and then we're going to do 5.7 and maybe even 5.8 today. They're both fairly short sections. But what can we do with this net change idea? Like where is it applicable? Like in economics, if C of X is the cost of producing a commodity, product, Then C prime of X is is called the marginal cost. And so if we do the integral of x1 to x2 of C prime of X dx, we get C of x2 minus C of x1, which is the cost of increasing production amounts from x1 to x2. So if we made 100 and we go, how much would it cost us to make 150? It's just like, what's the cost of producing that extra 50? So Preston, we did these last week. Another name for the F of B minus F of A is the net change theorem. We're just giving examples of in different fields of where this is used. So this is like an economics version. Economics, if you go down the rabbit hole, is filled with even Calc 3 shit. Integration over a couple things. If we had a reservoir of water or a container, the volume of a container at time t, or if V of t equals volume at time t for a container, then V prime of t is the rate of change a fluid flows into the container. Assuming it's positive, it means it's going up, which means the volume is going up. At time t. This blue pen sucks. Then T1 to T2 of V prime of t dt is Vt of 2 minus Vt volume at time 1, which gives us the net volume of water added over that time.
Why I don't use the
Because we're looking at a rate of change, and so like the volume V of t is just the volume. So V prime of t is going to say how that volume is changing. And we're looking at like if water is filling the tank, how much water has filled the tank over a specific amount of time. Now, if it's like a nice shaped tank, like a cylinder or a cube, calculating that is pretty easy. But not everything has a nice shape. Like some silos are funnels. They make like a circular cone. And so like the volume going up from like trying to look at the side of the container going, the water went up this much. When it's a cone, how much volume that is intuitive on other things, but this shows it. Now, the next one, you might shake your head at, but it's actually like leads to one of the primary equations in endgame mathematics. And this one's over like the mass of a rod. So let's say we have a rod like this. And this is A and this is B. And maybe the mass is changing. It gets thicker, it gets denser. It seems weird, but trying to picture a physical rod do this doesn't really happen. But like water in a pipe can be compressed at one end, and then you would have a different density or different mass at each end. So having a different mass in the same amount of volume, mass over volume, leads to the idea of density. Density is related to this. Density is usually given by, it's pronounced rho like that. It's like a curly or cursive looking P. And it is the derivative of the mass function. And so you can find the net change in mass from one end to the other, doing the integral from a to b of m prime of x dx, or a to b of rho of x dx. Since rho is m prime of x, it's m of b minus m of a. If you go through the full math sequence here, you will do ordinary differential equations. This is like the last class here. Like one of the next two classes, when you transfer in like this same idea, is called partial differential equations. So rather than ordinary differential equations, you're doing partial differential equations, which means you're doing stuff with more than one variable. In this case, x, oftentimes it's x, or like position, and t time. How does shit change? How does the position change as time changes and shit like that? And one of the major equations for that comes from this mass idea. So it leads to places. The next one is actually a segue into 5.7. So we're going to talk about if S of t is the position function of a particle, then S prime of t, the change in position over a change in time, is the velocity function. And the net displacement of the particle, well, that's actually just called displacement. The displacement of the particle from t equals t1 to t equals t2. And the reason I use displacement is this is like the net change in position. So like if you're on like if it's just on like on a road, like said, let's say it's a fucking car. and it pulls forward, goes forward 20 feet, but then it backs up 7 feet. The net change is 13 feet. Make sense? So that's why it's called displacement. That's how much it's shifted from its initial position. But the total distance it's gone would be the 20 plus the 7. It's 27 feet. So if you want to find total distance and not just displacement, then you have to take the absolute value of that function. That will give you total distance traveled. And since there's absolute values there, I'm not going to give it some magic formula. We're going to look at this. This is the topic of 5.7. Rectilinear motion revisited. Last time we did rectilinear motion, we were only doing derivatives. Now we're throwing in integrals, and we're going to see how that changes shit up. Anyone need this up longer? Okay. I'm gonna throw a box around this. This is total distance traveled, and this is displacement. Because those are both 5.7 ideas. Now, when we first hit this topic, we started with the position. We said, all right, if we know where we started, and we know where we stopped, and we know how long it took to get there, we could figure out the speed or the rate of change, the velocity, stuff like that. And or if you took that to the next level, if you knew your starting velocity and your ending velocity, and assuming like a steady rate of acceleration, you could figure out what the acceleration was. We're going to go the other direction. If you start off knowing how much the acceleration's changed, you can figure out how much the velocity's changed. And you figure out how much the velocity's changed, you can figure out how much the position's changed. So we knew S of t is position. V of t, which is S prime of t, is velocity. And A of t, which is S or V prime of t, which is S double prime of t, is acceleration. That's going in the order of derivatives. Now let's go the other way. If I have a of t and b prime of t, and I integrate both of these with respect to dt, then the integral of the acceleration is the velocity function plus some constant. And the same thing goes with integrating velocity. Get you the position function. Maybe I'll say C1 and C2. If you have this and C1 does not equal 0, then when we integrate acceleration, if we wanted to integrate it twice, like we're going to integrate it once and then we integrate it again to get to position, we have the integral of v of t plus c 1 here dt after the first integration. So you do the inner integral. And this would give us s of t. If we integrate c1, it's a constant, so we would have c1t plus c2. In fact, in physics, when you take physics, you will see this. In fact, you have seen these. When we did the rectilinear motion in the first place, we talked about something going up and then down, like a ball going up and down. And the height function was like, it would have -1/2. I'm going to say g of t squared plus v of t plus s. These are usually different numbers, but g is acceleration by gravity. So if upward is positive, acceleration is downward. V is velocity, and if it's positive, it's going up. If it's negative, it's going down. And S is, well, maybe I should put S naught and V naught. Velocity at start and position at start. That's why whenever you see height functions, there is always a fucking t squared with some negative number. It's accounting for downward gravity. And if you take the derivative of this, you get the velocity. This is a position function. Take the derivative, you get the velocity function. Take the derivative again. H prime of t is negative. We bring down the 2. We've got negative gt plus v naught, which would be v of t. And if I do it again, that shouldn't say negative g of t, it should say negative gt. Do it again, it's just negative g, which is the acceleration function. And so that's what I was saying, if you work backwards, you start with acceleration, you integrate it, you have acceleration plus some velocity constant, and you integrate it again, and you got C1 and C2. Here, the position thing is just in any direction. This is specific to something in a gravity field. Now, the really interesting stuff with this doesn't happen when shit moves in a fucking straight line. So the really interesting stuff where you're doing this integration, finding changes in position stuff, is when you get to calculus 3, when you're working with three-dimensional space. But for now, let's just pretend we're driving a line, like a car going in a straight line. It does have a displacement. So let's look at some examples here. This is a terrible fucking example. Suppose a particle moves with velocity v of t equals sine of pi t along a coordinate line. I don't think I need the word coordinate line. It could just be any line. Assuming that its starting position s of 0 equals 3 at t equals 0, find its position function. Now, before we actually dive into it, I want to point out something. You can see at t equals 0, we have sine of 0. At t equals 1, the velocity at 1 is sine of pi, which is also 0. But from t equals 0 to t equals 1, I'm going to use subscripts right there. We have sine of pi of t is greater than 0 because it's between 0 and pi, because the angle is between 0 and pi. So it's moving in a positive direction. But then from t1 to t2, sine is negative. And then t2 to t3, sine is positive again. So it's moving like back and forth. This is more like the motion of a pendulum. If a pendulum moved in a straight line. It doesn't, it moves on a curve, but So we're gonna go ahead and work with this. We want the position function. The position function is gonna be the integral of v of t. So we're gonna do that. I'm just gonna leave in generic a and b right now. This is doable without a substitution, but I swear to God, it makes my head big just fucking trying to. I have to stop and really think about what's going on. This problem gets a lot easier because the pi is fucking it up, right? We know the integral of sine. The derivative of cosine would be negative sine, so the integral of sine should be negative cosine. But the pi is fucking it up. So you might just do u equals pi of t, and du equals pi dt. So dt equals pi over, or du over pi. Then when you integrate this, you get the integral of sine is negative cosine. We've got negative 1 over pi. Cosine of u, but u is pi of t plus some constant. But we're doing it from a to b, so I don't need the constant. Cosine of b pi minus cosine of a pi. I factored out the negative 1 over pi because it's on both of them. Now, if we do this from 3 to 0, we go from 0 to 3, we're still going to get that negative 1 over pi cosine of pi t, but now we're going from 0 to 3. And we get negative 1 over pi cosine of 3t, or 3 pi, minus cosine of 0. What is cosine of 3 pi? It is negative 1. So if you're sitting there thinking about it, you're going like, okay, here's 0 pi. We go around the circle, we got 1 pi. We go here, we're at 2 pi. We go again, we're at 3 pi. So yeah, it is negative 1. Cosine is negative 1 on the x-axis to the left. Cosine of 0 is what? 1. So negative 1 minus 1 is, we've got negative 1 over pi times negative 2. So 2 over pi. In fact, looking at it from this way, because it is good, like going around a circle, we should have the same thing if we do 0 to 1. We get the same thing. So the first loop around just cancels itself out. Guys ready for some more? Actually, let's take a 5-minute break. Matthew just took a break, so here's a good break point. It's been almost an hour. That way he's not missing part of the lecture. And it is. So let's say our velocity function is 3t squared minus 6t. We're going to do a displacement and b total distance on both of them. 0 is less than t is less than 3. A should be easy for you. Go ahead and give A a try. Remember, displacement is the integral of velocity. And you're doing from 0 to 3. Make sure needing a nudge setting it up. What's the integral? Without evaluating, how it's just the integral of 3t squared.
T3 minus squared.
T cubed minus 3t squared. Then we're going to evaluate that from 0 to 3. So we have 3 cubed minus 3 times 3 squared minus 0 cubed minus 3 times 0 squared. Look at that shit. That's 27 minus, this is 0, minus 0 is 0. Doesn't look like it's moved. We don't have a velocity. Because it's net displacement. It's moved, but it came right back to where it started. Which means part of the time this was positive, and part of the time this was negative. So total distance changes it up. We're doing 0 to 3, but now we need to do the absolute value of 3t squared minus 6t dt. And this requires us to remember what absolute value means in terms of functions. So as a reminder, does anyone remember what this means? How we break apart absolute values so that we don't have absolute values anymore? This is some algebra shit that most people kind of block out. So if f of x equals the absolute value of x, if x is greater than 0, it just equals x. If x is less than 0, it equals negative x. Well, that's usually not how we write it. We usually write x if x is greater than 0. I'm writing it all funky. That's how we write it. So absolute value of x is that way, which means we need to figure out where does this change signs. Because when it's positive, we're going to leave it as is. When this is actually a negative value, we're going to make this negative instead of having absolute values. So we could do a number line. Like, where is 3t squared minus 6t greater than 0? Factor out a 3t, I've got t minus 2. Pick some test points. Less than 0 doesn't matter because we're only looking at 0 to 3. So we don't care about that. So we've got different values between 0 and 2 and 2 and 3. Which one is negative? If I stick in a 1, this is 3 times negative 1. This is a negative region. If I stick in 2.5, 2.5 times 3 is high. That's 7.5 times 0.5. That's a positive number. I don't know what it is. 3.75, it's positive. So between 0 and 2, it's negative. Which means we're going to break this up into two integrals. From 0 to 2, it's negative, so we're going to apply the negative x from 0 to 2. So I'll just do this. And then from 2 to 3, it's positive. This will get us the total distance it's moved. So this is negative t cubed plus 3t squared from 0 to 2 plus t cubed minus 3t squared from 2 to 3. You guys with me? So I'm going to write them all out. Let's see, we've got negative 2 cubed plus 3 times 2 squared minus negative 0 cubed plus 3 times 0 squared. That's my first one. And then I'll change colors for the second one. Here I've got plus 3 cubed minus 3t squared, or 3 times 3 squared, minus t cubed minus 3 times t squared. Okay, so this was 0, and this is 0. That should say 3 times 3 squared. So that ends up being 3 cubed minus 3 cubed. This is 0. The only two that really matter are these two. This is negative 8 plus 2 squared is 4. 4 times 3 is 12. Then I have a minus 8 minus 12. Four minus negative 4 is 8. So while its total displacement was 0, it actually moved 8 steps. 4 away and 4 back. Yeah.
Wait, was our starting position 3? Or was it 0?
0. We're doing from 0 to 3.
Okay.
Well, our starting time. We didn't actually say where it started. We just were saying how much has it moved.
Explain one more time why we did two integrals or two distances.
Because we saw the displacement, it moved back to where it started. Our displacement was 0. It actually moved. We know it moved, it had a velocity. I could put in values for t, like when t equals 1, velocity is 3 minus 6 is negative 3. It had motion, but it hasn't moved. So the displacement, which is like how much is it shifted from where it's at, was 0, but we know there was movement because it had the velocity. So doing the absolute value accommodates for those negative regions. When we're integrating this, I'm actually going to show this to you on Desmos. This might be easier to see on Desmos, where I can graph it quickly and accurately. Oh, I got 2 minuses in there. So we can see from 0 to 3, it's actually the velocity is negative. And from t equals 2 to 3, 3 is way up here. At t equals 3, the velocity is 9, but when t equals 1, the velocity is -3. So there's a change of velocity. Instead of looking at the velocity, when we do the area there, this area between 0 and 2 offsets the area from 2 to 3. In fact, perfectly. Which is fucking crazy. So I'll draw that pictorially in a second. On the graph, it's easier to show that by hand. But if I do the absolute value, I can now see what the velocity looks positive all the time. And so I can just track its movement that way. Yeah.
I was gonna say, couldn't you like kind of eyeball it once you know that its velocity goes negative? It's like its displacement is like 0, but you know the velocity changes, so wouldn't you be able to tell that it's gonna minus itself to get like your total distance?
Yeah, well, the total, yeah, but can you tell that this total is going to equal 8, going from 0 to 2 up to t equals 3? Because this is just the velocity. So like the position, the 8 that we got, when we calculated, was the change in the position. So the velocity, it was going, it started off at 0, so a negative velocity start off means the fucker threw it in reverse, said, oh shit, I'm going backwards, and then fucking started accelerating, like got to t equals 1, realized I'm going in reverse, and said, all right, time to start accelerating. But he still got a negative velocity, and so until he gets to t equals 2 seconds, he's basically slowing down his reverse, and then he guns it forward. But like translating that to position isn't all that intuitive. Like, would you have gotten 8 looking at the graph of that? No. So, but like graphically, what's going on there? Because you just saw it, so I'm going to sketch it kind of freehand here. This had some value in here. And this had some value right there. And the area, if this is A2 and this is A1, it just so happened that A1 equaled A2 in this example because displacement was 0. And displacement being 0 means A1 plus A2 equals 0, which means one of them has to be the other one, or the negative of the other one.
Yeah.
But like figuring out how much it actually moved, not so much. But if you look at absolute value, you can see that now it's tracking. We're getting, when we did absolute value, this shifted to looking like this. So now we can add these two areas together and they're not canceling each other out. So now A1 plus A2 does not equal 0. And we can actually figure out how much it moved. And the key to doing the absolute values is this. So you got to figure out where the function is 0. Oh, well, that's a starting point. You're finding where it changes value. And there's another way of finding where that changed value. No, that was it. That was good. That's where the sign change was. And then you figure out where the negative regions are, where the positive regions are. Flip the value. It was 3t squared minus 6t. 0 to t was negative, so I just had the same thing, and I threw a negative out front. You could change the signs here and have negative 3t squared plus 6t, but I recommend doing it in the parentheses like this first. That way, when you're later on going, what the hell did I do? Like, why do I have negative signs? It becomes a little bit clearer why you did it. It helps you, it helps me, like on a test, it would help me. Did that answer your question with the absolute value? Like seeing the positive, how it had a positive region?
Yeah. So to find, I guess, x, you set the function to 0.
To find out where I changed signs, yeah.
Okay.
We also had, I actually just gave you this a little bit ago. I realized I had my notes later on. I wrote it as 1/2 at squared plus v naught t plus s naught. Where for us, a was negative g. This was the height problem. A was negative g. And we saw the velocity function is just v naught plus at when you take the derivative. And this is assuming constant acceleration. So to do this, a is acceleration, and it needs to be constant. Like the gravity field for Earth's gravity, g is constant. Otherwise, if the acceleration is changing, or what's causing the acceleration, I should say. So, example. There are spacecraft that have constant acceleration. Spacecraft with solar sail. That's constant acceleration. And let's say that is a equals 0.032 meters per second squared. So like the solar wind pushes it. The particles from the radiating from the sun push on it and move it. We actually have things that work like that on Earth. You can see them on Earth. I just saw one at fucking Thanksgiving. It fucking tripped me out. Never seen it before. It was called a radiometer, I think. The way it works is it's a piece of metal. One side is black, one side was white. And I don't know if it's just paint or what, but like when the sun hits one side, it doesn't do anything. When it does the other side, it causes pressure. And so the fucking thing would spin. As the sun shined on it, if it hit it at any angle, it would start to spin, and it kept the spin going up. And so you would have something sitting in. The dude had it like hanging. We had Friendsgiving, I didn't even go to family, but they had like an ornament hanging from their kitchen window. And the fucking thing is a clear ornament, and the fucking thing's just perpetually spinning inside of them. How the fuck is it still spinning? Like, what's causing perpetual spin? And they're like, oh, it's called a radiometer. I think I'm spelling it right.
Doesn't the color black like absorb light? Isn't that why?
One of them, yeah, one of them absorbs light, one of them reflects light. And so one of them, I don't know which one's causing the pressure. Like absorbing it, if the black is absorbing it, it's not the one. It's moving with the white side because the reflection of the light equal and opposite force. That's gotta be if white, yeah, white reflects. That's why wearing white clothing is cooler. I think it's spelled right. Okay, but let's say starting velocity was, I don't know, 10,000 meters per second. Clearly, this wasn't when the spacecraft launched. That's pretty fucking fast. 10,000 meters per second is the equivalent of 10 kilometers a second, which is fucking fast as fuck. Kilometers, what, like close to 2 miles, or am I doing that backwards? So you're looking at, either way, even if it was miles per second, just think 10 miles per second. Over a minute, you've gone 600 fucking miles. Over an hour, you've gone 36,000 miles. That's like around the fucking earth in one hour. I don't know the diameter, that circumference of the earth. I know across the US it's about 3,000 miles. I'm picturing it can't be too, like maybe 12 times that going around the earth. I'm estimating. I think it's around there. I'm estimating based on the size of America and the way it looks on the globe. But from here to New York is like 3,000. So you're talking about circling the earth in a fucking hour. That's some motion, but it's accelerating. So like, what's its velocity after 1 hour? One day. 1 year. How fast is this motherfucker cooking? Let's figure it out. We know V of t is V naught plus AT. V naught is given as 10,000 and A is given as 0.032. I'm going to integrate this from 0 to x, where x will be, x is number of seconds that we're counting. And the reason why I'm doing X rather than picking numbers is that way doing the 1 hour, 1 day, 1 year gets a lot easier. All I gotta do is convert those to seconds, which is gonna take a calculator at some fucking point. But then it's just plug, well, it's definitely gonna take a calculator. We integrate this bad boy, we got 10,000 T. Plus, if we divide that by 2, we got 0.16 T squared. Evaluated from 0 to X is 10,000 X plus 0.016 X squared. So if X equals 1 hour, that's that 3,600 seconds, 60 times 60. That feels right, 36 and 2 zeros. Oh, this is what I did here. It gives us position. How much has the position changed? We can do the velocity thing in a second. Since I already have position out. What do we got here? 10,000 times 3,600 plus 0.16 times 3,600. Squared. That's got 6 zeros. And what is this one? That should be 0.016. God damn it. Times. So over 1 hour, the acceleration hasn't changed it that much. And so the acceleration has only added this little bit in the position change for 1 hour. After 1 day, though, $3,600 times 24 is 86,400. So we're going to do 10,000 times 86,400. Here I've got 864 and then 6 zeros again. And now we have measurable acceleration. It's not small. So the position's gone up, like without the acceleration, it would have only been 864,000. With the acceleration, it's moved up like another 12%. After a fucking year, I'm just going at 365 days. Not mentioning like there's a quarter of a year, there's some shit going on in there. Like in seconds, this is 86,400 times 365. So that is 31,536 seconds in a year. That seems like a lot of seconds. But if I multiply that by 10,000, this number's gonna get pretty big when I square it. From there, 13, that's, I need 9 zeros here. After a year, the acceleration has accounted for so much more distance. This is in millions, billions, trillions, 15 trillion from the acceleration, only 31 billion from the starting velocity. So that very, very marginal acceleration over time rapidly changes the speed of the, or position of this vessel. If we look at V of t, $10,000 plus 0.32 times 3,600, that was 1 hour. Not a lot. After a year, though, that should be another zero in there. 0.032. Oh, that's 536. The velocity went from 10,000 to 1 million. So that slight pressure from the solar wind after a year is making that motherfucker just book. Is hauling some serious ass.
We include units in final.
Yeah, this should be meters per second.
Said the way we solved it was for position.
Doing the integral gave us position. The integral of velocity is position. If we just wanted to see the velocity change, starting velocity, ending velocity. This would give us the starting velocity, ending velocity. Because like if we wanted net change in velocity. I didn't do net change in velocity, but if we want net change in velocity, we could do the following. Let's look at that. Like how much is the velocity? I was just looking at the numbers and going, well, look. But net change in velocity, we talked about doing net change in something means doing the derivative or integral of the derivative. So it'd be the integral of v prime of t from 0 to x dt, which is going to be what I had. Well, actually, yeah, v prime of x or v of x minus v of 0. So the net change, like over a year, is the 1,019,152 minus 10,000 is 1,000. Did I have the right number there? Yeah. Solar cells do a lot. After a minute, after an hour, it doesn't seem like it's a lot. After an hour, it's noticeable. It was about 1/8 larger. No, that was after a day. After an hour, it wasn't really noticeable. After a day, it was noticeable. I bet if you did after a week, you'd have a good chunk there. All right, 5.8. 5.8 is not exciting at all. It's on average value. Or mean value. If f of x is integrable on a to b, then the average value of y or f of x on AB is f average is 1 over b minus a times the integral of a to b f of x dx. What does that mean? If we wanted to, like this has an area like this, if we flattened out the area, it might look something like this, where that would be the average value. This value is f of a. This value up here is f of b. But rather than having one big awkward area, you have a rectangular area. It's kind of like leveling out how much the growth is. And it's based on b over a. I can show you how they come up with it if you're interested. We break up a of x into a bunch of partitions, x of n partitions. So a is less than x of 1, which is less than x of 2, which is less than x of n minus 1, which is less than x of n, which is b. That's b. So average value, you guys have seen this, add up the chunks, add up values over total values after number of values. That's a general value, the way of describing average or mean. In this case, f average is f of a plus f of x sub 1 plus f of x sub 2 plus dot 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 plus f of x sub n over n, because we broke it up into n regions. Does that make sense so far? What I'm going to do is I'm going to multiply this by b minus a times 1 over b minus a. And you might ask, why the fuck would we do that? Well, first off, this equals 1, right? If I put it, so I haven't changed the value. What I can do though is I can factor out that 1 over b minus a on bottom. And then I'm going to write the top thing as a sum. Maybe I'll call a x0. We're going from I equals 0 to n, f of xi. And what I have left over is b minus a over n. Does that make sense so far? So this part is the summation. And this part gave me the b minus a over n. But b minus a over n is delta x. Take the distance and divide by the pieces. Remember doing this? Back on that Riemann sum, boring fucking shit. And this was the definition of the integral.
Does it fix subscript K thing?
Yeah, that's stuff.
Is that gonna be on the test?
No.
I was doing it last night, I was like,
No. Some teachers like to do it, but like most students in this class. If anything, or engineering or something like that, maybe physics, something like that, not pure math majors. You're caring more about the application and how to use it, and Riemann sums are how it was formed and the derivation of it. If you want to be a math major, you should get good at that Riemann sum shit.
man,
Let me change that. If you want to be a pure math major, if you want to be a cool applied math major, you won't care about Riemann sums, just like I don't care about Riemann sums. Don't tell your other math teachers I said that. They all love fucking Riemann sums. So, how can we use this? This is also not going to be on your test.
I'm thinking U subs on this, right? Like
U subs are next. U subs are Thursday.
Oh, really?
Yes. Not all problems are easily done with it, so we're gonna expand on what we do.
We're gonna have sigma notation.
No, that's part of the Riemann sum category to me. This chapter is mostly on integrals. Integrals and definite integrals and indefinite integrals. I've done a couple little substitutions throughout this. Like when we did the sine of pi over t, I did a substitution, but I kind of like didn't do a lot with it. That was a minor one. We're gonna do more substitutions on Thursday, then I'll have a review ready for you guys for the test that's on Tuesday. There's a test next Tuesday on chapter 5. Then on Thursday, we'll do a final review. And then the following Tuesday is final exam. We got 2 weeks left. And 3 of those 4 days are tests. 2 of those 4 days are tests.
Wait, there's a chapter 5 test 2, like the following Tuesday.
Yes. So like timeline wise. It's the 28th. We're gonna have a test on November 5th or December 5th. And then the final is on the 12th. On this Thursday, we're gonna do 5.9 with the U substitutions. And a cleaner way of doing it. I will have the review ready for you. I'll write my own. I borrowed last time I borrowed another teacher's review, and that thing was fucking godforsaken. It took me like fucking 12 hours to do all the goddamn problems. I can't imagine how long it took you guys, those that did them all. They weren't easy. Like figuring out what to do was not easy on the review. The test was easier than the review. If you did the whole review, you would have seen that. I'll have your guys' review, at least the problems ready by Thursday. I should have them worked up and the solutions up by the weekend, early weekend. And then we'll have a test on Tuesday. So test on the 5th. On the 7th, we are gonna review for the final. So just like a quick recap. What we've covered this semester. I'll have more final review problems for that. With an answer key. As a reminder, I am in the Mesa Center from 8 to 11 or 9 to 12 on Saturdays. Over in Visalia. So if you want to grind some practice in before the exam. Let's look at an example with this F average. Don't. From 9 to 12 a.m. on Saturday. It will be both this Saturday and the next Saturday. So the Saturday right before the final also. If you want to do something fun this Friday night, Friday Night Lab, they're doing the derivative B. And they're giving out cash prizes. to like top 3 places. Now, even if you don't compete, you might enjoy watching others compete. So, find F average for f of x equals 1 over x squared on 1 to 3. Pictorially, what do we got going on? When x equals 1, f of x equals 1. When x equals 3, f of x equals 1/9. So my picture doesn't do it justice. We are looking for where is the average value? So we can make a rectangle that had the same area. So we're going to do 1 over b minus a times the integral of that. From a to b. So 1 over 3 minus 1 times the integral of 1 to 3, 1 over x squared dx. This is x to the negative 2. So what is the integral of x to the negative 2? We got to go up a power. So what's up a power? -1, and then we divide by the power. And we're evaluating that from 1 to 3. I'm going to move this negative. I'm going to put it out here. So I'm going to get -1/2. And I've got, so this is just 1 over x. -1/2. 1 over x from 1 to 3. So I have 1/3 minus 1 over 1. Positive 1/3. Which is 3/9. So if I were to do that picture a little bit better. That's 1, that's 3, that's 1 right there. That is 1/9 right there. The average value is 3/9, which would be right here. At 1/3. So apparently, if my picture were better, this can't be a good picture. There's no way. This part offsets this part. That's how I know my picture is shitty.
Where did your x go when you integrated it? Like when you put x to the power of. Oh,
I made it 1 over x.
Okay, yeah. Sorry, I didn't see it.
That's okay. It's a good question. So it's only 1/3, which is 3/9, which is like. It looks like the way I drew it, this is much bigger than this, but apparently those two should average each other out. That way we would have the average value. How can I figure out where that value occurs at? What is this value? That's a question mark if you can't tell. Well, f of question mark should be 1/3. But f of question mark is 1 over question mark squared. Because we're using f of x. So question mark squared equals 3. So question mark is plus or minus the square root of 3. Clearly, this is the positive square root. Which is like what, 1.7? What's the square root of 3? I clearly didn't draw this because mine looks like 2 pictorially, doesn't it? What's the square root of 3 though? 1.73. So maybe this should have been over here. 1.73 is question mark. And that way, I guess it was a little bit more like that. If I drew it better. Those two offset each other. That's it for today. We got 5.9 left on Thursday. We'll look at doing USEB's a little cleaner. We're gonna see what happens when there's a function in the limit of integration. Like we've been going from A to B, but what if like B is like x squared? What do we do if there's a function in the limits of integration? So that's something else that we're gonna cover on Thursday. Good stuff. Have a good day. Okay. Yeah, when will you be here? Oh, okay. I am on campus.
Or I
from-
mean, this week works.
You're gonna be ready this week? Probably not. I would say shoot for Monday. I'm on campus from like 2:30 to 6 on Mondays.
36.
Does that work for you? Anytime in there?
Eight? No, actually at work.
Or we can have you just set up something in the testing center, or you want to meet on like Sunday at like a Starbucks or something like that and give it to you. You work on Saturday or Sunday?
I do, I just don't know my hours. Can I, let me give you.
Yeah.
See, what I would have to get. See if I can find
I have no idea.
because I don't. That works.
I bet you do.
Well, just like the grading system.
The grading system is on. Let's take a look at it. I'll put it up on the screen.
Well, like I know what I need to get past, but like, I like.
No, I know exactly what your question is. I just don't remember what my percentages are. So I'll look them up real quick. Not what I want. I want canvas. What's up, Preston?
I just wanna ask, so like how homework's gonna work for the final, is it? So you only get the extra credit if you have done all of the homework up to the final, or do you get partial?
You'll have partial for what you've been doing.
But it'll be applied to the final? Or-
Yes.
Oh, okay, alright. Well, that's great.
The fuck? Okay, so tests are 75% and finals 25%. So You've got 4 tests. So tests are. Final is 25%. So you know that 0.75 times T1 plus T2 plus T3 plus T4 will give you your test points. And your final exam will be 0.25 times the final exam score. Add those up. F. You already know your scores for those 3. If you want like greater than 70%, you need this to be above 70. So you won't know these, but like you'll get to whatever this is, you're gonna have 0.75 T4 or final exam plus 0.25 final exam equals 70 minus. Another way of doing this is 3/4 times T1 plus T2 plus T3. You can calculate this part. Just plug in values. A little bit of algebra. This is the one class you should know how to do that.
So
Most people don't think about it.
I do have a class on Monday, till like 3:30 in Visalia. So that probably wouldn't be ideal since I've been lacking on attendance in that class.
Wait, what?
Monday, so Monday, and then I work 5 to 9.
We're Friday tonight. Okay. What's your work schedule over the weekend? Or when are you getting back?
I'm getting back Thursday afternoon.
So do you want to do it Friday? That Friday?
That works. Is that okay?
Yeah.
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 Where would we do it? Like Mesa Center?
From 1 to 5, I'm gonna be in John Muir, like 223. The computer science class is taking a final on that day.
Okay.
So
1 to 5?
yeah. And I'll email me or text me, and I'll give you the room number. I'll remind you next week, or even ask me about it Thursday night next week. So the room will be quiet, and it's 1 to 5 on a Friday. I don't know.
No, that works.
They're testing, so it'll be quiet in there as well, so you have a nice quiet testing room.
All right, so can I come in at 1?
Yeah,
Okay, great. I appreciate you, Jones.